Hey guys, see that? That's an old Marine Service linear power supply, a 12 volt power supply. And I'm going to repurpose it for my station. I want a linear power supply. Let me show you something. Hang on. Check it out, man. Don't mind the sound of the dryer. Hope the family doesn't see me laying down in the laundry room. He'll think I've had a heart attack and died, which would be a pretty logical assumption. Sorry about the shakes. That's a switching power supply I built. Each module is 5 volts at 40 amps. I turn them each down to exactly 4.6 volts. Gives me 13.8 volts out at 40 amps. And the thing is, it's continuous duty. But it's a switching supply. Hang on. That's right. Back in my shop, man. Hang on, I got something to show you. Okay. What's going on, man? What's up, Lucy? Laying around? Yeah, that's what I've been doing all day too, man. I don't know what was wrong with my mind when I was in the garage last time we looked at Lucy, but that is for the strut lines that will go down to support the boom. Check it out, man. I think last time you saw the yard, it was a foot deep in snow. About 2 weeks ago. They say March comes in like a lion and goes out like a lamb. That's usually true in Michigan. That little pile there, it's about 4 inches high. That was 4 feet deep, man. And that's where I stepped off the deck and went down. And we only got one other little pile of snow. And then we'll take a look inside that power supply, okay? I'll show you what's inside. Oh yeah, I got to deal with that branch that was hanging from my end fed, don't I? Oh, another little surprise. So, I want to show you what's inside that Marine power supply, made by Numar, N-U-M-A-R. And I'll tell you my plan for it, and I want to show you the metering that I built for it. Okay, hang on. Hey guys, if you don't mind, I'd like to show you a project I've got planned that I want to get on pretty quick because I'm sick of my switch mode power supply hash. It's not always terrible, but it can be. It's usually not audible, but sometimes it can really tick you off. So this is an old Marine 20 amp 12 volt power supply that I'm going to remake into my new station supply with the same specs. That's what it is. And I'm going to be using the case, the transformer, and the pass transistors on top. Those are TO3 style NPN transistors, all mounted in parallel. And they should have, if it's a decent design, a slight ballast resistor in the emitter lead of each one, like 1/100 of an ohm, or something on that order. I don't know. But I want to talk about that briefly. I'm going to take the cabinet off and just let you look inside. Mainly interested in your thoughts on the overall project. And I want to show you the metering that I built for it. There's the expanded scale voltmeter. And I'm going to put you on a tripod. And this is the box of parts. I finally found it. It's got everything I need, man. Nice fused IEC connector. It's got the binding posts and everything. Let me dig the amp meter out, and I'll set the camera on a tripod. Okay, hang on. Okay, You guys got to bear with me, man, because I'm half scared. I can tell, man, because I always get out of breath. My adrenaline's just flowing right now, man. This is the little board that drives the expanded scale voltmeter. Just a little quick knockoff using whatever junk box parts I had on hand. I'll pause you again and zoom in on the meter. Hang on. Okay, that is the expanded scale voltmeter. It's designed to run with that switch mode power supply. And you might see that it says Lana on the lower left-hand corner. She's my granddaughter. And the current meter, the amp meter, has my other granddaughter, Lola. So you can see that the needle won't start moving until it hits 10 volts. I'm going to show you how that works in a schematic after we take a look inside the power supply cabinet here. Okay, hang on. Okay, I felt guilty. I can't cheat little dear little Lola like that. That's my amp meter. Again, it's designed for that switch mode power supply, which runs 40 amps all day long and only gets mildly warm. Okay, so let me take that power supply cabinet apart and we'll look inside. Okay, hang on. Ooh, check it out. I was wondering about that. The first peek inside. Look at that monster electrolytic cap. Whoa, hang on. Alright, so check this. Man, hang on. I thought leaving you on the tripod would be a grand idea, but it just made you swing back and forth like a pendulum. So there's the power transformer, obviously. It's pretty beefy. Its specs, who knows, but it's capable of running 20 amps, and it's rated for marine duty, so hopefully it'll be adequate. I'd like it to be a little higher voltage. 12 volts is not its open circuit voltage. Please note, it's probably on the order of 16 or 18 volts. I haven't measured anything, but I will when I get into it. But it's fine. If I can only get 12 volts out of this thing with that transformer, that'll work. Yesu's happy with that. So this is where the two electrolytic capacitors are bolted in. And by the way, boys and girls, you never want to touch your fingers across an electrolytic cap, lest your hand get blown apart. But this hasn't been powered up in decades. So let me pop that printed circuit. Oh, by the way, those are the 3 emitter ballast resistors I spoke of. So let me pop that board off and let's take a look at the filter caps. Hang on. Okay, check it out, boys. Damn. That's a cap. That's an electrolytic cap. Now, and when I'm done, it's going to have even... Come on, man. Oh, come on, man. It's going to have even bigger ones than this in it when I'm done. 36,000 microfarads at 40 volts. Yeah. Yeah. That's going to make a fun project, man. It really is. Okay. I want to talk to you about expanded scale voltmeters. So if you have no interest in electronics, in electronic theory, you should probably bail. I'll try not to be wordy. I'll try to get to the point. I used to do professional level in-services. It's hard to believe that I'm doing this level. It's not a tutorial. It's not an in-service. It's just a show and tell. Okay, man. Hang on. Couple things I neglected to show you. That is the original scale for the 2 meters that I used. They're 50 microamp meters. eBay specials, but they're not the cheapest ones I could find. I tried to find a reasonable meter, and I like them. They're nice. Second thing, man, seems like every time you step into the land of arcs and sparks, I scare the shit out of you. Today is no exception. Dear frickin' God. You know what I mean? Okay, guys, hang on. Let me prop up my my scribbage. Hang on. Perfect. Let me put my glasses on. I thought you'd like to know that I'm sitting behind you, trying to get my shit together. So this is by far the easier of the two schematics, because there's basically nothing to it except for a piece of wire, right? This is your meter, and this is your shunt resistor. In my case, I used a piece of 14 gauge THHN and experimentally determined the length from here. Actually, if that were a bare wire, you could take this lead and just slide it along your shunt wire while drawing a known current until your meter reads correctly. Well, I did it experimentally. I forget how long that wire is. I could measure it if anyone's interested, but it seems like it was like, I don't know, 11 inches long. And I'm going to pause you. Note, a couple notes for those contemplating making silly show and tells. If you're using a liquid gel pen, don't go over it with your highlighter, thus, because that'll happen, okay? Nothing else to note there. Let me tip you down. Hang on. Okay. And if you wanted to know the resistance of that piece of wire, this is how you would determine it. You would take the full scale reading that you wish your meter to display. Let's say you want your meter to read 0 to 20 amps. Divide that by the full scale current rating of the meter movement, and you'll come up with this factor. Now then, you divide the resistance of the meter movement. In my case, I'm assuming it's 20K. All right. These are what I'm assuming, and this is for an example. I don't remember what my meters were as far as internal resistance. I know they're 50 microamp full scale. But anyway, let's say that they are, you can measure this with your own meter, your DMM. Let's say you measure the meter and it's 20K. Okay? Divide 20K by this factor, and it'll tell you what value of shunt resistor you need. You could buy one. You can buy shunts. But in my case, I chose to use a piece of 14 gauge THHN for a couple reasons. A, it was free. It was laying around. And B, it's a fairly high power dissipation resistor. A lot of good airflow around that wire. And yeah, it works excellent for a shunt resistance. So I'm going to pause you and turn the page so that we can talk about expanded scale voltmeters. Hang on. Okay, that's the schematic for my expanded scale voltmeter in my power supply. And I've been using it in the shack there, on this and that, just playing around with it, and it's exceedingly accurate. It's dead nuts on, man. And I'm going to tell you how you can design an expanded scale voltmeter experimentally, okay? You take your meter. In my case, I knew what it was, okay? But let's say I didn't. Anything between, I don't know if a 1 milliamp meter movement would work here, probably. But we'll talk about that. So an experimental way to set this up, hook a pot in series with your meter. and a good high value one like 20K or something, and goes even better, put a 1K resistor in series with it first and then the pot, so you don't blow your meter up when you turn the pot all the way. But you can be careful. Start with a pot in the middle, 20K pot. Hook it to a known voltage source with your DMM so you know exactly what the voltage is. Adjust the pot until that reads the same. In my case, what I did, I wanted this meter to be 15 volts full scale. So I applied 15 volts exactly here. I adjusted the pot until it read full scale. Then I measured the pot and replaced it with a fixed value resistor. With my meter, a 4.7K series resistor produces an accurate voltmeter from 0 to 15 volts. Okay? So now we want to make that read, we want this to not move until we hit 10 volts. And here's how you do it, man. I used a 9.6 volt Zener Diode in series with a 470 ohm resistor for current limiting. You'd like to see 10 or 20 milliamps flowing through this Zener so that the rest of this circuit doesn't load it down. 10 or 20 milliamps. With that resistor, I get about, I forget what the math is, 25 milliamps maybe, with 12 volts applied. So what happens here is, let's say you start at 0 volts on the input. You start increasing the voltage higher and higher and higher, and this Zener is not conducting at all. No current flow through that Zener. When you hit 9.6 volts and then keep advancing your input, this starts conducting. And the voltage, once it starts conducting, the voltage at this point will always be 9.6 volts, no matter what this input voltage is, okay? And so let's say we apply 12 volts here. Minus 9.6 equals 2.4 volts. This resistor is dropping 2.4 volts across it. And so what I did, I took a pot, in my case I used 10K, slapped that across this resistor. So now this pot has 2.4 volts on it. I adjust the pot so that this reads exactly 2 volts. So with 12 volts applied, I read 2 volts. And you put a 1 in front of you put a 1 in front of it, in front of each of these divisions on the meter face. So 12 volts in equals a reading of 2 volts, and you put the 1 there, and now this is reading 12 volts. It'll say 12 volts. Do that for 13 volts. This will read 3 volts, but it has a 1 in front of the 3. 13 volts. When this exactly equals, I'm getting confused here. When this exactly equals 10 volts, this will exactly equal 0. When this is exactly equal to 15 volts, this will be equal to 15. That's it. That's all there is to an expanded scale voltmeter. Some considerations is loading. In the ideal world, this resistor value, this pot value, will be at least 10 times this value. And it's way more than that. A 5K pot might have been better there. It doesn't matter. And again, you'd like the value of this pot to be 10 times less than the combined value of that resistor and that meter, which in my case it is not, but it works dandy. It's dead nuts accurate across the range of 10 to 15 volts. Whew. I hope that makes sense. I hope that makes sense. It's about the best I can do. And since I'm on the subject, I'll show you what kind of overvolt protection my power supply will have. It's very simple. Hang on. Okay. If you guys have never seen how most linear power supplies achieve overvoltage protection, it's done like this, man. Very simple. If you don't know what an SCR or a TRIAC is, imagine a transistor that's off, and once you trigger it on, it stays on until you remove power completely. Okay? And you can use an SCR or a TRIAC, I believe. I've drawn the schematic for a TRIAC, but it could be an SCR symbol. It doesn't matter. Very simple, man. And the reason I wanted to show you this is because it uses the same Zener Diode principle. Let's say I want this thing to trip at 15 volts. I want it to shut down because something went wrong, And if this supply is designed to deliver 12.5 or 8 or 13.8, doesn't matter. If it ever hits 15 volts, something most certainly is wrong. And so this is the input. This is the power supply itself over here. You have a Zener diode rated at 15 volts. No current flows. But man, as soon as this hits 15 volts, this starts to conduct. It triggers. This goes positive. It triggers this device. And this is a heavy duty part. And it's connected to the output terminals with very heavy wire. And oftentimes it's mounted right on the output connector jack, binding posts, or whatever it uses. And if it ever triggers, it shorts, and it blows whatever current protection the supply has, whatever that may be, whether it be current limiting or a fuse on the mains, on the AC line, right? Yeah, that'll protect your rig. So that's the scheme I'm going to use in my supply for overvolt protection. I haven't decided on a form of current limiting or even if I'm going to build current limiting into it. Who knows, man? We'll see. Anyway, I hope this was of some value. I hope it was of some value, my babblage. And I feel sorry for you, but I don't feel sorry